It's actually an EPA requirement that surface waters be filtered, and that's a logical requirement. So here we have this technology that's been in use for a very long time, more than 100 years, and we're trying to figure out how it works. And so I want to take you down that path of exploring what might be going on inside filters. Okay, so we're going to talk about filtration model, which is about removing little particles using big particles, where the big particles are the sand grains, and somehow we're using sand grains to remove things as small as bacteria. Just a note about that. Slow sand filters were the first. The first sand filters were, of course, called sand filters, right? They were filters made from sand. They were called sand filters. And later on, we eventually started calling those first ones slow sand filters. And when those first sand filters were built, they didn't even have germ theory yet, because germ theory came along in the late 1800s. And the first slow sand filters were built around 1829. So that means that they built the filter to improve water quality, not knowing that they were trying to capture bacteria and other pathogens, and not having any idea how that filter was actually working. And yet, like, this is just one of these amazing maybe coincidences or just stroke of good luck, that it turned out that the filters made out of sand actually did remove bacteria. And that is the big puzzle. Like, how does a sand grain that's several hundred micrometers, so 0.2 perhaps millimeters in diameter, several hundred micrometers in diameter, remove an organism that is just 1 micrometer in diameter? So that's what we're going to puzzle out today. So these are some mysteries about filters. Filter pores are gigantic compared with the particles that they remove. There's something happening, we call it ripening, which gives a sense that there's something biological happening in these filters, like it's a fruit that tastes better after it's gotten riper. The filter somehow ripens and works better after working for a little bit. Although an insight that comes from that is that clean sand is somehow a lousy filter. And I'm just wondering if you're going to start maybe pulling things together from what you've learned already in this class. If sand is actually a lousy filter, what's the actual filter? What is actually filtering inside the sand? Another mystery, filters don't fail by clogging. They fail because particles start leaking through. So it's not because you can't push the water through anymore that they fail. They fail because particles start leaking through. So particles start coming out the bottom of the filter. And so I'm beginning to lead the witness. I'm beginning to lead you now. Flock filters have limited capacity too. Remember this from flock filtration, that the flocks in the flock filter, they can only take up so many small particles, and then they become less porous and they become useless because there's no more water flowing through that flock filter. So this is the similar kind of thing is happening in sand filters. And then another insight is that our mystery is that when the filter fails, as in particles start coming out the bottom of the filter, only a tiny fraction of the pore volume is actually filled with captured flocks and particles. So it's not because the pores get full that it fails. Something else is going on. And there's the question, what is happening inside those pores? So I want to share some results from some experiments that some students did a few years ago at Cornell. And this is just an overview of their apparatus. So they've got some water coming in. They're making the water dirty themselves. So they're adding clay to the water to make it dirty, a clay suspension, not a solution. And that water is going through a turbidity meter so they can see how dirty the water is. And then they're adding PAC, which is the polyaluminum chloride, or the coagulant. That's being pumped in. It's going through a flocculator, and then it's going into the filter, and it's going into another turbidity meter so they can measure how clean the water is coming out. So they ran a bunch of tests, and this is some of their data. And we're seeing time on the x-axis in hours, and we're seeing effluent turbidity, so the filtered water turbidity. And you should know that they were filtering 5 NTU water. So the water going in was 5 turbidity units. And coming out, it's, I can't see exactly because it's way down at the bottom here, but it's something like 0.1 or 0.2 NTU. So the water leaving this filter would have met the EPA standards, which is 0.3 NTU. They noticed there was no clarifier in this schematic. So there's a flocculator, and then it goes right into the filter. That's called direct filtration. You can do this if the water is pretty clean so that the filter can actually handle all those solids. And in this case, that means that we know exactly how many particles are going into the filter because we added 5 NTU and all of them are going into the filter. Okay, and then they varied the coagulant dose. And so we get to see what happens as you vary the coagulant dose. And let's start with the very lowest coagulant dose that's on here, which is 0.2 milligrams per liter. That's these orange dots. And you see that it didn't perform real well as far as the turbidity was a little bit higher than the other ones, but it kept on working for a very long time. So that's interesting. And they didn't actually take that one to failure, like it was still working when they quit. And then we'll increase the coagulant dose a little bit more, go up to 0.65. Now we're the yellow dots, and look at this. Now it starts failing around 6 hours. You see that? The turbidity starts rising up, maybe a little bit before 6 hours, and it just goes up. And then we'll go to another extreme. We'll go all the way back to a very high coagulant dose, 1.55 milligrams per liter. And that one fails after 2 hours, and it fails very fast. That line is very steep. Turbidity comes up very, very quickly. So these are results from real filters. And the question is, well, what's going on inside the filter? And it's very similar to understanding what's happening in the flock filter, in that we've tried, but we can't really have cameras that show us exactly what's happening inside the filter in real time. And so we're left with watching what happens going in and going out, and then trying to figure out, well, what must be happening inside this black box of this filter? So here's my story of what I think is happening. So there's this idea that somehow the filter is slowly getting full, and in the end, particles come out the bottom. And that's the first insight, that particles are getting pushed deeper and deeper into the filter over time. And so maybe it would make sense that the particles are initially being caught near the top of the filter. And then as it continues on, the particles are getting pushed deeper and deeper into the filter until finally at failure, they come out the bottom. And so this is an animation that kind of proposes that. So that there's a filter off to the right on the screen. And I've got 2 graphs here showing head loss. So the pressure drop across the filter, head loss across the filter, and turbidity coming out of the filter as a function of time. And this is what happens. So head loss methodically just goes up linearly over time. Turbidity gets better and better. And look at the brown going down through the filter. That's like showing the filter getting full. And at the end, particles start leaking out the bottom of the filter. And we see that in the turbidity going up quickly as the filter becomes full. So this is really powerful, like this insight that, oh, particles are loading from the top of the filter, and then they're slowly filling in lower and lower. That's a really cool insight. And here's what we see in the course of time. There's this initial period when performance is bad. It's a combination of backwash, debris that was left from the previous time the filter was clean that might be coming out initially. And there's something about the filter loading and having something about it that's making performance better than if it were just clean sand. And it's something about the particles that are coming into the filter are actually improving the subsequent performance of that filter. The turbidity coming out slowly decreases over time. Do you see that? This black line slowly drops. It's not a huge drop, but it slowly gets better. And this is commonly seen in filters, and it suggests that the removal in the brown zone, where the filter is supposedly like full, that particle removal there is actually better than in the clean zone that's at the bottom of the filter. Because think about it, at the beginning of a filter run, most of the filter is clean and a little bit of it is dirty. And that doesn't perform as well as a filter that is mostly dirty and has a little bit clean at the bottom. That means that the dirty part of the filter is actually doing a better job of filtration than the clean part of the filter. So that's comparing the loaded zone and the clean zone. And in the middle, there's this active filtration zone where it's actually very effective, where particles where most of the particles are being captured. And then the filter goes through what we call breakthrough. Breakthrough is when the turbidity or some of the particles start showing up in the effluent, coming out the bottom of the filter. And I'm postulating here, you should know this, I'm talking about filtration models in this lecture today. And these are models, these are hypotheses, these are things that we're just barely understanding, that we're still hoping to learn more about. Here's a hypothesis that maybe the large flocks get to the bottom of the filter first because they have a hard time, because they're being pushed the hardest by the water, because they take up more space, there's more drag on them, and the water is pushing them the hardest.